There we go. All right, now we're getting folks joining. I'm just going to give people a moment to jump on. Hey, everybody. My name is Kevin, and I'm the training coordinator here with the Association of State Floodplain Managers. And I want to welcome you to our CTP information exchange for this month. And this month's topic is the National Water Model. Before we get into that, I just have a few brief admin announcements for what to expect today, and a note about some of the follow-up materials after the webinar. So first thing, just to let you all know, we've got a pretty big group here today. We are not going to be able to take questions by unmuting our lines and verbally submitting questions. So if you have any questions or comments on anything you see today, use the Q&A window in the webinar software here. And that way we'll be able to see it come in, and we'll take as many questions as we can as time allows, especially at the end. There's going to be a dedicated Q&A portion. If we miss anything, we're going to make every effort to get you an answer to that question or comment after the event. So if you send something in and it doesn't get addressed during the live event today, don't worry, we'll try to make sure we get that answer to you in a follow-up. Quickly, just wanted to note continuing education credits. This event is eligible for continuing education, and you'll get that by participating in the entire event today for the full 90-minute duration, and also by answering some of our poll questions. So we've got a mix of quizzes and just kind of gauging your feedback. So look out for a few of those and make sure you weigh in when the time comes. We also are going to send you certificates of attendance. If you need those for any other professional purposes, we'll be sending those directly to the inbox, to your email inbox, and it's going to take about a week to turn those around. So toward the end of next week, look out for your certificates of attendance for this. As you can see on the screen there, if you have any interesting topics you think might be a good fit for this webinar series, please contact Alan@floods.org, and we'll get that into the mix for consideration. Now with that, I want to turn it over to Alan Liloff, who's the Flood Science Center Program Manager here for the Association of State Floodplain Managers. Alan's going to talk to you a little bit more about the CTP Info Exchange and our topic today, as well as the speakers. So Alan, take it away.
Good day. I'd say good afternoon, but some people might be on the West Coast. So hope we're having a good day. Yes, this is a webinar series we do quarterly. And the ASFPM has been long a supporter of the Cooperating Technical Partners Program, and actually created a Cooperating Technical Partners Subcommittee of the ASFPM Mapping and Engineering Standards Committee. And that is co-chaired by Daryl Rockfield with the state of Missouri, and Dave Gannett with the state of Maryland. And you can see the goals here of this subcommittee, and one of the major things that we try to provide is provide some information exchange, and that's what these webinars are intended to do. So we have quarterly webinars that are appreciate the attendance that people for those webinars. So today the topic is the National Water Model, and we have two really good speakers. We have Brian Cosgrove, who works with the Office of Water Prediction, a part of the National Weather Service, which is responsible for hydrologic research and operational activities. He is the technical director for the National Water Model, bringing new versions of the model into operation and connecting with end users to improve the products and services. Dave Gannett In addition to being co-chair of the Mapping and the ASFPM subcommittee, CTP subcommittee, Dave works for the Maryland Department of the Environment. He has been with the Maryland State NP coordinator for 20 years and has been the state's floodplain mapping coordinator for about the same time. During that time, he has led Maryland's efforts to restudy and create geo-referenced models for virtually all of their detailed floodplains, AE zones, and upgrade all of their approximate A zones to model-backed best available data models. And recently, Maryland has completed a 100-year base flood elevation plus 3-foot GIS data set to convey resiliency in tidal and non-tidal floodplains across the state. So with that, welcome Brian to the first topic.
All right, thank you very much, Alan. I appreciate the introduction. Let me start sharing my screen here and welcome everybody. All right, and I'll just double check that from Alan or Kevin that you guys can see.
Yeah, looks good, Brian.
My slides. Okay. Okay, so hello everybody. For the next 40 minutes or so, we're going to be talking about, as was introduced, the National Water Model. Specifically, I'm going to be giving a background overview of the model, so explain what it is, some of the products that we output, and basically how it's being used, and also some future directions. So as you heard in the introduction, I work for the Office of Water Prediction, which is part of the National Weather Service, which itself is part of the National Oceanic and Atmospheric Administration, or NOAA. So that's sort of where we reside within the federal government. So if we get into it a bit, the National Water Model. You can basically think of this as a CONUS-wide, so a country-wide, high-resolution model whose focus is water. So you're probably very familiar with different weather models. Some of you may have heard of the Global Forecast System, or GFS, which is the main weather model we use across the country. So a lot of other finer scale models too, and other domains. So if you sort of take that conception of a weather model and then translate that to water, that's what we have here and what we'll be talking about. Compared to weather models, which have been around for decades, the National Water Model is actually very young. The first version was installed or implemented just back in 2016, so about 6 years ago or so, and it's still growing and being enhanced every year. So it's really revolutionizing how hydrologic guidance, such as stream flow and other output, is developed and delivered. And one key phrase that you hear again and again from me is complementary. So the information provides complements, existing sources of information. There are already forecasts of stream flow and soil moisture, snowpack, and other fields out there. And what we're doing with the water model is providing another source of this guidance, and you'll see how it sort of fills in the gaps in some of the existing information that we already had before. If you look off to the right side of the slide, you can see around 3,600 points where the National Weather Service outputs official or produces official river stream flow forecasts. These are produced by the River Forecast Center spread around the country every day. And it looks pretty dense, but if you were to zoom in, especially say to the western US, but even into the eastern or southern US, if you zoom in enough, you start seeing big gaps between those dots. And what we're doing is with the National Water Model, is to provide really dense, high resolution, kind of seamless coverage for the whole country, which you can see down below. And we're filling in the gaps in between those official forecast points with this model guidance. So if we move on to the next slide here, this gives you a sense as to the density of the output for which we can provide stream flow and other fields. So here we have a zoom in into the North Carolina and South Carolina border, and around 3 million people or so live in this area. And the nearest River Forecast Center forecast point is approximately 30 miles away from some of the areas there. And you can see those depicted as the circles at right. So with this guidance from National Water Model, we now have an additional source of information that forecasters, emergency responders, floodplain managers and others can look at, where maybe prior to this, we did not have any information. This model provides info down to very small ungauged streams, headwater points, very minor areas that maybe look small, but during a big rainfall event, it could obviously swell and become threatening. So we're trying to fill in those spatial gaps, and we're also filling in temporal gaps. So our forecasts extend further in time than some other sources. And so sometimes they can give a good region scale, kind of regional scale heads up of conditions that are impending, say, several days in advance. Now, if we take a step back and see where this is operating, we'd look just at North Carolina, South Carolina, but in the last slide, but where we're running is actually over the entire United States, which you can see off to the right there, along with the Hawaiian Islands on the left and Puerto Rico and the US Virgin Islands there in the bottom left. The next version of the model, which we'll get to in a few slides, we're actually expanding to Alaska too for the first time. So southeastern Alaska will be covered by this model as well. So how does this all work? You can imagine that there's probably a lot of moving pieces within the National Water Model. And I think maybe the best place to start is in the top center of this diagram. There are a lot of data sets that enable the model to sort of conceptualize or depict how everything's linked together in the country. It needs to know how all the river reaches, each segment of a river are connected. It needs to know what type of vegetation is growing, trees, grass, et cetera, in a different area, what type of soil there is, and many other parameters. So we start with a stack of parameters as input. And then we also, in the upper left, read in a lot of weather forcing data or meteorological data, things like temperature and precipitation, other weather elements that can impact soil moisture, snowpack, and stream flow. We don't produce that ourselves. We read in that weather information from a suite of external weather forecast models and also some observation data sets like radar and other gauge type data sets. So all of that gets fed into the box at lower left, that kind of larger box in the lower left quadrant. And that contains what you might say are the land surface or hydrologic modeling components. Those models read in the inputs, so the weather forcing data and the parameter data sets, and they figure out how much of that moisture percolates down into the soil, how much of it runs across the surface, how the snowpack is building up as it snows, or how it melts, et cetera, et cetera. And then it channels that runoff into a river channel. Once it reaches the river, the model then takes that pulse of water and translates it downstream. It can go all the way to the coastline. Once it's there and once it's done that, we're able to visualize the contents of the stream channels across the country. So stream flow, stream velocity, and all the kind of preceding products such as soil moisture, snowpack, evaporation that went into that. We won't go into this too much, but this slide is basically just highlighting the different parameters that we have to read in. So again, off to the left, the first column is our network coverage, or basically how all the rivers are connected. In the third column over, reservoir representation, we have a basic representation of reservoirs or lakes, water bodies in the model. And that's key because you can imagine that having a lake or a reservoir in the middle of a stream, it's obviously going to really impact the stream flow. And that's an area of active development where we strive version over version to increase the realism with which we model these water bodies. Off to the right there is just referencing that we have a lot of continual land surface parameters, vegetation, soil types, etc. That again is really key to kind of underpinning the model. And then the reference to gauge snapping there in the upper right. We read in a lot of data from USGS stream gauges and US Army Corps of Engineers stream gauges. We actually assimilate that data or draw those observations into the model to correct the trajectory of our model and improve our own forecast. So we read in many of hundreds, thousands really, of those gauges. So I mentioned we read in weather information to force the model, and this would include temperature, humidity, wind speed, pressure, radiation, and precipitation. Precipitation being the most important there. You can imagine that would have a extremely impactful presence or influence on stream flow in the model. And then we draw these bits of information from many sources. So you see a lot of acronyms listed down below, everything from the high resolution rapid refresh or HRRR weather model, all the way to the North American high-res NEST model or the NAM-NEST model and others in between. We read in observations from the multi-radar, multi-sensor or MRMS radar data set and some other data sets. So we draw in weather forcing data from quite a wide variety of sources. We feed that through the model, and what comes out the other end, I've mentioned a little bit, but here are just some images of it: soil moisture, stream flow, surface temperature, evapotranspiration, snowpack, and then a kind of a different one in the upper right. Whereas the other ones that I just mentioned are raw outputs that come directly from the model. Flood inundation maps or inundation are post-processed type of product. So the model runs, it produces raw output, and then we have a completely separate set of processes separate from the national water model that produces these inundation maps. The way the two things are linked is that the flood inundation mapping, or FIM is the acronym, these FIM maps are produced based on the stream flow from the national water model. So that's sort of the linkage there. So the water model simulates stream flow, and that is then passed off to a separate set of processes to generate these FIM maps. We consider that to be sort of a holy grail of some sorts in terms of these flood inundation maps, getting them available across the whole country. You could imagine that would be a valuable resource for emergency managers and other applications to know where to pre-position supplies before disaster happens, maybe to get a situational awareness of what's happening during an event, and then afterwards to figure out, okay, where did it flood? Where was the most damage? Where might the most help be needed? So that's something my office is working on quite a bit, again, based on national water model output, but also based on some output from the river forecast centers across the country and other federal agencies, basically creating these aggregate FIM maps based on the best source of available information. So that's just a bit of an advertisement of what's to come. It's not available quite yet, but it will be starting in around a year. So where can you get water model data? How can you access it? There's a few sites that are listed here. Water.noaa.gov in the upper left will give you access to clickable maps, a point and click where you can zoom in on a specific stream and get the model's output, simulation of analysis or forecast of a stream flow and a stream reach. You can zoom in all the way to your backyard if you wanted to. Now, the caveat here, of course, is that just like with weather models, this is a fully automated model. There's no sort of human forecaster in the loop. This should be treated as guidance. It is not the official Weather Service streamflow forecast. It's another piece of information that can be used to complement existing sources of information. Perhaps most valuable is the raw data itself. So the raw output from the water model, and it's in a net CDF format. You can download everything the model produces. So soil moisture, stream flow, everything between, from this NOMADS distribution site. This is an operational site. It's there 24/7. This is the official sort of distribution site for the raw data, and all the different file types for everything that we run are available there. And then off to the right is something new, just an advertisement coming out in spring of this coming year, well, 2023. This is a new service called the National Water Prediction Service, or NWPS. It's going to feature output from the official River Forecast Center produced river forecasts, but also feature forecast or guidance from the National Water Model. So both sources of information will be available on the NWPS early next year. So just kind of a heads up, I guess, about that. One other area of access that I wanted to mention is this set of experimental products that you can access right now. weather.gov/OWP/operations, address is listed there at the top, will bring you to an access page that provides you with the ability to take a look at several different products that we're currently accepting comments on. These are experimental products that we are hoping to move into operations, but they are currently, again, experimental and are in a comment period, a feedback period. So they include some visualization services where you can take a look at some derived products, so not just sort of point and click stream flow, but value added products such as arrival time. When will what we call high flow or bankful flow arrive? How many days from now? What's the probability of that occurring? Might there be rapid onset flooding, or basically a very quick increase in stream flow above a certain threshold occurring? What's the chance of that occurring? So if you dig into the visualization services, you'll be able to access some of these sort of derivative products. There's a National Hydrologic Discussion, or NHD, which is the text-based discussion you can see there at right. That just gives a sort of a verbal overview of the hydrologic conditions across the country. The AHD, or Area Hydrologic Discussion, highlights particular events occurring right now of high impact. So it zooms in geographically and then basically highlights concerning situations, ongoing flooding, the potential for heavy rain to cause flooding, things like that. So you would go to the AHD to see if there's something of high importance occurring right now or for the next few hours. And finally, the Flood Hazard Outlook, or FHO, that is going to give you sort of a continental scale look at flooding probabilities or likelihood over the next several days. You'll see down the bottom mention or reference to FIM, or flood inundation mapping, and I mentioned that in the slide or two ago. It's targeted for public release starting the end of the next fiscal year. So by the end of September of 2023, we are looking to have 10% of the country covered with FIM maps that are publicly accessible. And then by 2026, we'll be expanding that to nearly 100% with sort of a ramp up in between. So the goal here is to, again, provide these inundation maps on sort of a ramp schedule starting at the end of next year. So I've mentioned a bunch of inputs and outputs. I've mentioned what is sort of inside the guts of the water model, how it works. So this slide deals with how we run it in operations. This is a 24/7 model. It's got high uptime reliability. It's not meant to fail at all. And the way we cycle this in operations is laid out in this table. So we have an analysis cycle, which is basically a snapshot of current conditions. This is run once per hour, and it assimilates USGS and US Army Corps of Engineers streamflow data to basically correct our estimates of the current streamflow and give us the best possible sense of streamflow across the whole country. Then we have 3 different forecasts that are kicked off from that analysis. So you can picture the analysis running every hour. And then once per hour, we kick off a short range forecast, which extends out to 18 hours. So this would give you an 18-hour forecast that's refreshed once per hour. The CONUS medium range ensemble is a 10-day long forecast, and that's produced 4 times a day. And then we have a long range ensemble down the bottom, which is a 30-day forecast produced 4 times a day. You can imagine that as you go further out in time, things get more and more uncertain, and different forcing errors and model errors creep in. But this is sort of the overall operational cycling that we have over the CONUS, over the continental United States. Off to the right there, you see Hawaii and Puerto Rico. We have a similar cycling there. We have analyses as well as a short range forecast out to 48 hours. And we also have Alaska coming up in the next version, which is exciting, and that has analyses, short and medium range forecasts. So this is basically the set of cycling that we do, and we produce stream flow and snowpack and everything else for all of these different types of forecast cycles. So as I mentioned, we began back in 2016. That was with version 1 of the model, and where we find ourselves now is 2021. Or 2022, I should say. We just put in version 2.2. That's what's in operations right now. And then in terms of future upgrades, we're finishing off development on version 3 of the National Water Model. That will go in the middle of next year, 2023. We have some exciting upgrades coming for that, which I'll get to over the next few slides. And then looking further beyond that, we're completely rewriting the software framework that our model uses kind of from the ground up. And that is going to be my final slide that I'm going to touch on, something called the Nextgen modeling framework. That's going to unlock several different exciting improvements in forecast accuracy and efficiency, which we'll get to. But for now, let's take a look at what's coming next year. This will be likely summertime next year. This is Water Model version 3, and perhaps the biggest improvement or enhancement is with the first time total water level forecasting capability. So what do I mean by total water level? Basically, this is going to be, if you live along the coast, if you're one of the 100 million people who live along the coast, this is the type of guidance that's really going to help you out during an event, such as the current hurricane, for example. Along the shoreline, you can imagine that flooding is not just from the rivers or from oceanic influences, but it's the combination. And that's what we call total water level. So it's fresh water from river flooding plus storm surge, plus tides, plus wind impacts, so all of that combining to basically push the water up onto the coastline and cause flooding there. And that's for the first time what we're going to be able to provide around the full coastline of the United States, except for the Great Lakes, plus Hawaii and Puerto Rico. So the way we're doing that is the graphic at right, and you'll see the coastal model, or module, I should say, which is part of the National Water Model in the middle. And that's going to draw in freshwater discharge from the water model. So basically, river forecast from the water model will enter into this new coastal module. Weather forcing data, and also some oceanic water level forcing data. All that gets combined into a prediction for water level along the coast. So what would that look like? In the upper right here is just a really rough test map that we produced a few weeks ago. This is for Puerto Rico. This is for Hurricane Maria. And you can see the land is sort of the white area at the bottom, the ocean's up the top. And then the coloring is the water depth along the coastline. You can see that the water is pushed into the land area. And again, what this capability is doing for us, it's combining the river kind of freshwater flow with the impacts of storm surge, tide, and wind, giving us that total water level impact. We can display it as a time series. The dashed lines are the observed high water mark with kind of a plus or minus margin of error. The black trace is the total water level output from the National Water Model. So, you know, we would hope to see that our peak corresponds with the peak of the high water mark, you know. So we're doing pretty well here in some early test runs. Here's some other traces. And we're looking at multiple cases. Here's Hurricane Laura. And again, we can create similar test output. And we can look at time series traces. Again, how do we compare to the high water marks? And these were tests done during the development of the system, which we're finishing up right now. And we're currently taking a look at additional verification and looking at how to effectively package up the data. So this capability is coming again next summer and is just about fully developed. Something else for the next version of the model is a new Alaska domain. So up in Alaska, you can imagine it's a challenging environment to simulate. And there are cold land season processes there, glaciers, river ice, deep snowpacks, permafrost. You know, it's a pretty different environment to model. And so we're building some of those capabilities into the National Water Model for the first time. And you can see here, the domain is the yellow area. This is kind of the catchment areas off to the right there. And we've been working really closely with the Weather Service field office there, the River Forecast Center over there. We're going to, in fact, be ingesting some of their forecasts and assimilating that into the National Water Model for glacial dam outburst floods. So that may be a new term. I know it was to me. And basically, this is when there's a glacial lake, you know, perhaps sealed off with a bunch of ice, and then the pressure of the water or some melting just lets that lake sort of burst forth. There could be a lot of you know, excessive stream flow from that, a lot of destruction, and we're able to read in the forecasts from the RFC, the River Forecast Center, to improve our forecast of that event. We're going to have around 390,000 stream reaches that complement the existing official sites in the bottom left. So if you go there right now to the official Weather Service River Forecast page, you'll see those sites in the bottom left. We're going to be complementing it with the image at right, which is the stream network that the water model will be providing guidance for. So you can see the difference there. Here's just an example of us assimilating in the Glacier Dam Lake forecast from the RFC. The black line is the observation. The blue line is the Glacier Dam Lake assimilation, and that is basically our simulation if we take in information from the River Forecast Center. And then the red is if we don't read in anything, if we don't assimilate any data from the RFC at all. It's basically a flat line because the water model doesn't know about the glacial lake, doesn't know that there's been an outburst flood, and so it just simulates basically a flat line. Obviously, that's not good, and that's why we're taking in forecast information from the River Forecast Center. So another enhancement is that I'll speak to our improvements in model forcing data. You can imagine that if the rainfall is off in what we're reading in, there's no way to get an accurate forecast. You know, if it's a rainy situation. Too much rain can cause too great of a flood. Too little rain obviously is going to cause too little of a response. And so we're constantly looking for improved sources of not just observed precip, but also forecast precipitation. So what's coming along next summer is the introduction of a new forcing data set called the National Blend of Models, or NBM. This is basically a National Weather Service product where they've taken information from across several different weather models and, in this case, precipitation, and have blended it together in a statistical fashion to come up with an improved precipitation forecast. You can see an example of that in the lower right. In the upper left is what we're currently reading in, a sample of data. So the lower right is what we're adding, and you can see some higher resolution, and in general, it has higher accuracy than the raw model data that we use now. So that's an exciting enhancement, and we're expecting some forecast improvements from that, from ingesting that new data. Some additional enhancements coming. So we have an updated land cover data set. This is important because the flood responses, the runoff responses really depend on the condition of the land surface. Is it forested? Is it urbanized? Is it bare rock? This changes over time, of course. And if we're using an older data set, we're going to have an incorrect kind of notion of that land surface condition. And by bringing us up a bit more close to present, so this is a 2016 data set, we get more accurate representation of that. Now, obviously, you can have some big dynamic impacts that occur very rapidly. For example, wildfires. If you have a wildfire move through, that can completely alter the hydrologic response of an area. It can lead to hydrophobic conditions, basically meaning that when the rain's falling, it's going to just sheet off and not be able to sink in or infiltrate into the soil column. So what we've begun to do is add the capability for dynamic parameter updates. Basically, we've laid the groundwork for, in future versions of the model, being able to alter the model's knowledge of what the soil type is or vegetation cover is to reflect different types of events that have happened, like wildfires. We've also changed the land surface model physics to better represent impervious conditions. You might encounter them, bare, bedrock in some areas, but this is also really focused on urbanized areas where there's a lot of imperviousness. And we've adjusted our infiltration processes there to improve that accuracy. Now, I should say that this is not, the National Water Model is not it's not a hyper-resolution model. It's not a kind of a hydraulic model where we can, at this point, include impacts of urban drainage. We don't have storm drains. We don't have culverts. It doesn't know about railroad tracks or overpasses. It doesn't have that level of detail. And so we're working towards that in future versions where we would implement hyper-resolution or extremely finely detailed versions of this model. But for now, we just have bulk representations of urban environments. We've also changed the runoff module to something that can more accurately simulate the way that water percolates down or runs off the top of the surface of the soil column. So calibration, one of the improvements we've also made is to come up with an improved set of parameters or a way of tuning the model's parameters. The model comes prepackaged with kind of a basic set of parameters describing the soil and vegetation, but those are rough parameters that need to be cycled through the model and compared with the model output being compared against observations again and again to come up with an optimal set that optimizes the skill of the model. And we've done some work on that to come up with better ways to tune the model, basically to adjust the parameters to improve stream flow is what we're really trying to optimize. And so we've seen some great strides with that, with version 3 coming out next year. I already touched on down the bottom, the National Blend of Models. What we have also coming up then is the use of observed precipitation over Puerto Rico for the first time, the middle of next year. And so that'll be a great enhancement as well. So I want to spend a few minutes now talking about where we're going after 2023. So we're advancing our operations by using a completely rewritten framework called Nextgen. It's the Next Generation Water Resources Modeling Framework, or Nextgen for short. And I think the key component is illustrated at the bottom left. Right now, you can imagine that with the current water model, we treat the whole country as sort of a monolithic modeling element, in that the whole country is modeled by one land surface formulation, if you will. We vary the parameters and we vary other components, but at the root of it, it's basically one land surface model inside of the water model that's taking care of soil infiltration, for example. So one of the key advances with Nextgen is that we're going to be able to vary the selection of the physical model or land surface model inside of the National Water Model Framework. We can vary that spatially. So you can imagine if you have a desert area, that might mean that a certain model might do best there. If you have a forest area, maybe a different class of model will do better in that area. And so you can begin to create sort of a patchwork quilt of different treatments or different modeling treatments within the overall umbrella of the National Water Model. This quilt would basically vary spatially at a pretty high resolution across river catchments. And so we would be selecting the most appropriate model that performs the best and is most appropriate for the processes going on in these different areas. So how is this going to lead to operational improvements? Well, so forecast accuracy, first of all, will be improved because, again, we're going to be selecting the proper physics for the different areas. So snowpack, for example, if we're modeling in, I don't know, southern Florida, we don't need to be running a snow model, for example. And so, we'll gain efficiency from that, not having to run that sort of model. Again, there will be different models that perform better in certain areas. And so we can sort of mix and match and come up with that optimal blend. The framework flexibility also gives us the option to run ensembles. I would say that overall, just as in the weather community, the hydrologic community is moving towards ensemble forecasting. So we're moving away from deterministic forecasting, where we have one forecast, one conception of that, this is the forecast and this is the only way it can turn out, right? This is what the model is saying. Moving away from that and towards saying, okay, there's a lot of uncertainty coming from different sources. This is the envelope or range of forecasts that could possibly occur. And so you can generate an ensemble of that type through feeding in different sources of forcing data. You can represent uncertainty in different ways. What we're focusing on here is feeding in, creating an ensemble based on using different conceptions of land surface, so different physical models. So you can create a model-based ensemble. And in Nextgen, we're going to be able to do that, have different formulations over different areas, a few different options for each area, and hope to capture the uncertainty associated in the hydrologic modeling in that fashion. So some closing thoughts. I'd say that the water model really is advancing, as I mentioned in the beginning on the first slide, it's really advancing operational forecasting, research, commercial applications, everything from federal continental scale applications down to neighborhood scale applications in a way that we haven't been able to before. So the way it's doing that is by providing sort of seamless coast-to-coast information of different types and at different spatial and temporal resolutions than we had before. Again, it's complementary information. So there is a wealth of very valuable, extremely accurate information out there already. And what this is meant to do is to add to that, so as you're taking a look at your existing sources of information, this is a new source that you can consult as well, perhaps filling in gaps in terms of the types of information offered or providing information again for locations where there was just nothing before. This is a young model, like I said, so 2016 was version 1, and we're rapidly improving it version over version. So it's a foundation that we're building on. We just put in the most recent version in 2021, and then also this past year. We have version 3 coming up next year, and again, a lot of improvements for next year. We have Alaska coming online. We have the total water level or coastal coupling, which is coming online, looking at the combined impacts of storm surge and freshwater, wind and tides, all of that being combined into the total water impact. And beyond that, we also have derived products such as flood inundation mapping, which will be coming online in a public fashion over the next several years, starting with the end of next year. So all of that are together kind of encompass some exciting developments coming along. We're also actively developing the Nextgen system. So again, that's a new framework that's going to underpin the National Water Model that's coming out in 2025. It's going to give us enhanced accuracy, improved efficiency for modeling, and just open up the ensemble and capabilities. So the last bullet really summarizes it. The steady upgrades to skill combined with the improvements to visualizations and products that I mentioned plus the partnerships, I think, with all of you and other end users and community development are really going to continue to advance this system. So, with Nextgen, it's a community-based system first and foremost. It'll be fully publicly accessible through the GitHub code hosting system. Everybody's welcome to contribute to it and look for applications for it. And even before Nextgen comes into operations, we have all the publicly accessible output from the National Water Model, and we are always looking for feedback on that. So anything about the accuracy of the model, good or bad, any types of new output that you would like to see, any ideas for how to package it, more effectively, any ideas for partnerships too. All of those are elements that we're always very keen to hear back from all of you on. And so after this seminar ends, I'm definitely happy to get feedback from you, and we can continue the communication. So with that, I'll say thank you. Just for this part of the presentation, we'll have more that Dave is going to cover in a little bit. Before that, though, I think we have a poll question that we're going to get to before we continue on with the next presentation.
Yeah, thanks so much, Brian.
Sure.
I am going to open up a poll for everybody to weigh in on. If you could take a moment, it should be prompted for you now. The National Water Model is best used for, and then pick the prompt that best described, finishes out that statement. And while you're all doing that, I'll just remind everybody that we are going to take questions at the end. So if you have any questions about anything Brian went over, please find the Q&A section of the webinar software here and send your thoughts to us. And Brian, I just have a couple of quick hitters. I know we'll do most of them at the end, but had a couple of questions from people come in asking about the FIM map kind of compared to the FEMA maps. And so I guess the questions are, to sum them up, what are the main differences between the FIM map and the FEMA maps? And then is there an eye toward replacing the FEMA maps with the FIM maps eventually, or what are your thoughts on that?
Right. So the first thing I'll say first and foremost is that there's really close coordination with FEMA and with other federal agencies too, because we do realize that there are several different sources of FIM maps, whether it's U.S. Army Corps of Engineers, FEMA, there's flood insurance maps, is all different sources. And so we're taking very sort of deliberate collaborative steps, with these agencies to make sure that what emerges is sort of the best product. But some of these agencies, and I see the results of the poll have come in, so it looks like most people have gotten the correct answer, which is great. I'll get there. Maybe I'll comment there in a second. There are some static maps that are available out there, say, where a 100-year flood is or a 500-year flood is that you can access, from FEMA or other agencies. What these FIM maps would be more of the predictive variety. So they would be based off of, the water model outputs, a 10-day forecast or 18-hour forecast. And they're also going to be combined with input from other agencies too. So we're going to try to be very careful to take sort of basically the highest quality source for different areas or different situations that we can, again, collaborating across federal agencies. So I think I'll leave it at that.
That's great. Thank you so much. Well, as you can see, and sorry if I kind of interrupted you by sharing the results of the little quiz here, but it does look like most people chose the third option, which is the correct one. Correct, Brian?
Yep.
Okay.
Yeah. So it might be tempting to replace the Weather Service river forecast with output from this model, but again, this should just be treated as guidance, would be the phrasing. So Weather Service forecasters would use water model output to create the official sort of aggregate forecast, right? So they're going to use water model input, they're going to use their own models, they're going to use data from other agencies to create sort of the official Weather Service river forecast. The water model output is more akin to raw weather model output, where you don't take forecasts from a weather model kind of as the official forecast. It's just simply raw model output, right? It's a source of information. The official forecast would come from a different, official outlet. And in terms of detail, it'd be tempting to look for forecasts and use them verbatim from a backyard, say, backyard scale. The model certainly operates down to that resolution, but there's so much uncertainty in terms of forcing data and landscape description and model errors that I would not, I would advise against that. And you can take that as an indicator. You could look for trends or, sort of basically a heads up of, impending wet conditions or dry conditions. You can look for regional signals. When does it look like at a regional scale it's going to start flooding, things like that. But I would not kind of peg a exact stream reach and put a bunch of faith at that stream reach level because there's so much uncertainty. And the last question was urban areas, I believe. And so that was one of the last options. And again, we have a rough bulk treatment of urban areas in the model. We are working on a finer scale implementation of the model down to tens of meters that would be able to take into account storm sewers, culverts, roads, railroad tracks, things like that. But for now, for this sort of stage the water model is in, it's kind of should be kept at sort of a higher level scale because again, we're not taking into account the built infrastructure in those areas.
Great. Well, thank you for that clarification and explaining that. And with that, I think we'll turn it over to Dave Gannett with Maryland. Dave.
Hey, thank you. Let me get my screen started. I kind of read through some of the questions and I kind of hope that my presentation will at least help explain some of that for people moving forward. Give you a little bit better flair for what the differences between this and the FEMA maps are. So let's see if this is going to work. Sorry. Is that opening up yet for you guys, Kevin?
Yeah, Dave, I can see your screen, but it's not in presentation mode.
Yeah,
That's
I noticed that. I'm trying to get it. There we go.
There you go. Looks good.
Okay, so Maryland was exposed to the National Water Model through our Silver Jackets program, probably right around 2016 or 2017. So we saw some benefits of trying to take this data and integrate it or use it with our FEMA floodplain mapping. So as a CTP, we've been doing floodplain mapping and we thought this was a great thing to take a look at, and we'll get into an explanation of what that project was for you in Maryland. Do you want to run the polling question for us?
Yes.
Second presentation?
Thank you for the reminder. Yes, I'll get that opened up. And this one is, have you used the National Water Model to predict flows in your state or community? In this one, we're just trying to gauge where all of you are at. So no right answer here, but please take a moment to weigh in. All right, I'll leave it open for just another few seconds. And let's see the results.
Cool.
There you have it. So most people saying no, but would like to, and varying responses across the board otherwise.
All right, well, that makes me feel a little bit better that at least people are considering it and moving forward. Okay, so in Maryland, our project, we had the people in the Silver Jackets team, the National Weather Service, FEMA, it was a CTP project, the Army Corps of Engineers, and our engineering for the CTP is wood. And we also used wood for their programming skills to build this connection to the National Water Model as we move forward. So what I want to give you a real quick flavor is I trimmed a lot of slides out that I knew Brian was going to have, but I think that I still needed to kind of pull them together for you. This just shows the gauges in the National Water Model and sort of on the same map. And if you take a look at that from that perspective, we wanted to combine the data that's from the National Water Model and our risk map products in Maryland moving forward. All right, so again, we're looking at mainly those two middle forecasts as the best results. We use the output from the National Water Model to help us format our alerts as we get into this. The hydrograph is not part of any of our output parameters in Maryland. But we are looking at using this with our team moving forward. And again, Wood has moved on from Maryland and using it for other states. They've done a lot of with the hydrographs and some of the flood warning tools, I believe, in Tennessee. And then even ASFPM, I've noticed there was an awful lot of presentations on the National Water Model. So I know people are taking a look at this kind of stuff moving forward. So what are we doing? Well, we're taking those forecasts from the stream flow forecast from the National Water Model on the left. We're combining those with some of our HEC-RAS runs that we use for our floodplain mapping, using the flood alert to turn on, like where we think the flooding is going to be, and then also then map it so that when we send out the alert, we've got a map that gives people a better idea what's going on. So a bad joke for you guys is my programming experience ended in 1977 when I dropped a deck of Fortran cards on the floor. Since then, I've done no programming. So from a programming standpoint, I'm not going to be able to explain it to you, but I can give you the concepts that we've asked our programmers to sort of pick up and run with. So the White Marsh project is northeast of Baltimore, just outside the Beltway in Baltimore County. And this area, when you look at a FEMA floodplain map, you get the National Flood Hazard Data Layer, just again above the I-95 corridor. And you get an idea that the water flows from the upper left to the lower right. And oh, by the way, in around 2015, these red dots sort of give you an indication of where we've had a lot of reports of flooding. So since we were doing the floodplain mapping at that time for Baltimore County, they didn't have an awful lot of good information in this area that seemed to be caught off guard. We thought the National Water Model was a pretty valuable tool for us to at least look at it as a pilot project here moving forward. The watershed's a little small, but yet at the same time, it's pretty extensive in what was there. The three orange dots near the center give you an idea where we had gauges. The blue highlighted areas with the cross sections across them give you an idea where we had FEMA floodplains and stream models that we have developed. As mentioned earlier, all of our streams and all our floodplain models are georeferenced, so it's pretty easy to take this data and sort of combine it with other data sets moving forward. And if you want to really get into the nitty-gritty of understanding what's going on, this chart shows you the 5 blue FEMA floodplain models that you would run for these streams in this area, for the 10, 25, 50, 100, and 500-year storms. So from a standpoint, we've got almost a chart that gives you an idea of flow parameters that could be, like based on some kind of regime of predictions through this area. Again, 5 of them are blue for FEMA, and we've added, with the core, we added about 8 or 10 others in between that to kind of bracket that and give you an idea of what's going on. So now you've got a list of 12 to 15 flow regimes. And oh, by the way, if you just look at the stream flow about 2/3 of the way to on the right, where you see under stream flow, can you see my arrow, by the way, Kevin? When I'm talking?
Yes. Mm-hmm. Yep.
Okay, good. So where the stream flow is, you can see that we've got an awful lot of predictions that are sort of bracketed by the FEMA floodplain mapping models. Well, if the National Water Model comes out with something, then we would just find the corresponding line that matches up with that flow. And oh, by the way, we've already run the mapping for it. So it's think of it as like you've got a sort of like a pre-cooked hamburger and someone selects hamburger. Well, then you pull out the slide for that and you give it to somebody. Here it is. So it's a little bit of information exchange between the National Water Model and where it fits on this chart. The other thing looking forward, this flag, we would probably, like this is how the alerts come into. You'd start to pick up when you wanted to alert somebody what was going on, with whether the action was a base flow, something is going on, a minor flow, and then get to moderate and a major. So these indicators are going to be very prevalent moving forward, okay? So again, we had HEC-RAS models moving forward, and at the beginning, we added the return periods to fill it out, and you end up with something that you can be able to move forward from that point. So the hydrology and the hydraulics are combined through the stream model forecasts and the flood forecast, that you actually get this dynamic grid of information for any of the streams for what's going on. So we've pre-run every stream for any number of those 12 or 15 different flows, and basically have them sort of stored in this environment. So when the National Water Model gives you something on one stream, you can combine it with something that was also predicting on another stream, and you get a dynamic flow regime that you can actually publish and release for emergency managers. So again, that starts with the details of downloading the data from the National Water Model, computing the stream flow forecast and things that we use for the regression equations that are FEMA maps, and then ending up with a map display for an inundation grid of what's going on. This is all done in Python, and you can understand that the first step is the National Water Model gives you those predictions for the entire country. We can download those and then trim them out for Maryland. So you're actually setting that data up and just getting it down to something more usable, and then running the National Water Model data and using it to set up those sort of triggers that we just talked about on the other page. So again, you're getting the national forecasts, you're associating that with a return period that's already in your computed digest, and then building an export. So what that looks like is the stream flow forecasts are sort of on the left. You set up the alert system like I talked about with action, minor, moderate, and things like that. So you know that when any one of those streams in White Marsh get to a certain level, you'd at least want to trigger that someone should take a look at it. And then what that looks like when you combine them is again on the far right. So you've got static floodplain mapping. You're sort of building a suite of results that you're actually then publishing to make people aware of what's going on. Okay, so once you get to the point that you get to a moderate or major alert, you can basically then start every hour updating the data, pulling it from the data sets and figuring out what's going on. That works this way. We actually have triggers that sends out that alert. The alert goes out to somebody saying, hey, something's happening here, launch the flood tool. The email, when you open it, this is what the email looks like, and then you get some kind of simulation of the results that are out on the web page. The link then takes you to the web page where we said we have the dynamic mapping. The dynamic mapping walks you through a disclaimer that I'm agreed to the terms of the map, so you can't just use the data without looking at it, and you get an idea of what's going on in a particular area. So on the right, you can see a bunch of layers that are sort of show up for the user to turn on. Maybe the alert system gives you like 4 or 5 different flows to look at, and then you can sort of pick and choose and look at multiple flows moving forward. So again, you get a return, you get a result, and you get some data to take a look at on the fly. The newer versions, I think we're not stuck, but we started with one of the earlier versions of the National Water Model. And as a result of that, we're sort of not, we're not at the slide bar status like other people are. We're basically using the output to generate what's going on for that information. This kind of slows down those slides for you. You get an idea that you've got things that are going on through the email alert. It's telling you to go to the flood forecast map, and you can understand when the peak is, and you can see that the peak is going to happen 104 hours or 5 days from now. And then go to the forecast map and see what's happening at that point. Our splash page, I think I can slow this one down. The splash page uses dynamic or deep linking to generate the maps in sort of bricks or blocks. And you can see here that we have the blue floodplain on here for sort of base information, and then the different events will show up with on the gray shading of what's going on throughout that area. Again, it's based on a lot of other data. I can click on other data tools on the left-hand side and take a look at it. But I think this will walk you through some of I guess, sort of the output. So you got an alert, you can click on, it'll take you right to the alert that's turned on. You can look at other alerts on the right-hand side. see other maps and see other events. And then, oh, by the way, since we pre-ran everything and from the output standpoint, we know that when we get that line of code that hits a certain event, then we know that we've already pre-populated that event, even including the red buildings that are going to be flooded to make people aware of it. So it's a little bit more of taking the results that are coming out of the National Water Model and kicking them out here. So one of the things that we learned as we went through this process is that those alerts are not sensitive, but you've got to sort of learn how to, like be aware of them. If you set those alerts too low, then you're going to get, like 50 emails in one storm, because you've got the alert so low. So you kind of want to start to get rid of the noise and get an alert system that you're focusing on a certain parameter that you actually want to be able to take some action and look at what's going on. Just like the National Water Model, our system is set up to be kind of young. So even though we had a lot of the flooding events in the 2015 and 16 era, we really haven't had much happen in this particular area that had a need for an alert system, and yet it hasn't been proven through with an actual event that kind of matches it up moving forward. Because all our data layers are instead of or on a GIS map, we can add other data sets to that, like the building footprints, stream gauges. We link to those. Our SHA system has some road closure maps that we can turn on and off. Again, we can add additional data layers to the pre-populated event and just keep moving forward from that tool to sort of generate some output going forward to give you some idea of, hey, should I close this road? What's going on? So we have had one event. Well, let me go back and just say we have the ability to sort of save some of these forecasts if we get one that's big enough. So right now we're sort of doing this statically where we're going to save it. But then also moving forward, we'll probably be able to figure out a way to automate this and save these events. So now go back to the previous map, you get an alert and you want to see what's going on, but you want to see what's going on in relation to a past event that happened in 2015. You can say, hey, look, this is going to be, this is predicted to be worse than the 2015 event. So you can get a frame of reference by adding these historic events moving forward, okay? So we did have a event that triggered one of our alerts in 2018 from ESIAS, and it gave us some data that gave us a better idea of where those triggers should be. So we've at least learned from that and are moving forward, and we'll plan on applying those lessons learned moving forward. Some of the big lessons we've learned moving forward is that the programming, the data, the modeling, anything that we've done is scalable to anywhere in the state. So even though I've done this for one particular watershed, that means that every FEMA watershed that we have, we can potentially pre-populate at least the 3 or 5 FEMA flows and start this process. Again, you got to do an awful lot of coding in between, but at least you've got the framework to get there. We're completing the dam break modeling in Maryland for high hazard dams this year. We're generating the GIS flows and outputs for those. So think of that, instead of having the static FEMA maps, we'll be having the high hazard dams. And we think that this is a better way of combining or utilizing the National Water Model. It'll probably be our next pilot. Instead of 18,000 road crossings and all those extra data layers I've got to add, we only have 150 high hazard dams, and I think that we're going to have a little bit better, I guess, ability to get there from those two things. So look for us to sort of pick that up and run with that over the next year or two. Also, we kind of like share with MDOT and a lot of other things. They have vehicle mounted LiDAR. So now where I have a road crossing, that I have something that's important, if I can get their data set for the road crossings, then we can actually map the top chord, or I'm sorry, the road, the weir topping of that bridge, and understand, like what's actually going to happen, and we even pick up the sumps for that information. So instead of, like recreating the wheel and going out and resurveying everything, we have an awful lot of data that we can generate that. And then we can use that to update the actual road and stream crossings through the GIS location. So our data sets are 15 years old in some of our HEC-RAS models. And that's pretty old from in a GIS standpoint. And from that standpoint, if I say the word flip phone, you're going to think about the new fancy one, but think about the static flat flip phone from 15 years ago. That's about the technology we were, that it wasn't an iPhone. It basically allowed you to send text and, like take a phone call. So about this time of the static flip phones is when we started this process. So our GIS tool to collect the bridge data is probably plus or minus 30 meters, which isn't very good, which again, I think using this vehicle mounted LiDAR will allow us to improve that process and kind of update the maps. So we want to continue to evaluate what's going on with the National Water Model and some of the updates that Brian has shown us today, figuring out where that's going. As I said, some of the presentations I've seen at ASFBM includes a slide bar. We don't have a slide bar, but we think that's a little bit easier for people that are novices to GIS to use instead of our tool with the data layers sort of clicking on or off. We've completed a 100-year plus 3-foot data set. We think we should add that to the map to give people some perspective on risk and whether this is, how does this relate to the national flood maps and also, like what's going on in the forecast. So we'll probably expand our pilot to other watersheds, select other high risk areas to complete another pilot or do something in that relationship. And this year we're working with FEMA on more weather tools using our CTP funding probably this year. So the Maryland Department of Emergency Management is also purchasing a MesoNet weather network this year. They'll be implementing those weather stations over the next 3 years. So that'll be another data set that we could add into our tool and get a better looking at this. And then again, going back just 3 to 5 years, you kind of were stuck with the hardware that you had to store this data. And we think we can probably improve the data processing faster using the cloud. Some recommendations, even if you go back 15 years, if you collect your data and all your models in a GIS format, you can always leveraging them and layer them and combine them with other data sets. Talking to other state agencies to understand what they're working on to leverage their resources is a big idea. You can even go back to scour reports if you want to geo-reference them. There's an awful lot of bridge information and culvert information and scour reports moving forward. And then I think this is the biggest one, is to look forward. Weather's changing. FEMA standards are based on mapping, which is historic data, and typically look backwards. So these weather patterns for resiliency, you kind of want to have something that shows you what's going to happen moving forward and what those potentials are. Those higher flows can come in any time. You need to be aware. And then communities that are using the National Water Model that I'm aware of are using this because they've already had a flood and they're kind of want to have a better tool to sort of get in front of it. And but I think these times, these tools need time to be prepared and apply. So you got to spend a little bit of time up front before the flood, and none of us know when that's going to happen, even with a hurricane going on today. So I'm going to stop there. We can open this up to questions for everybody, and I'm going to stop sharing my screen. Kevin, it's on you.
Yeah, fantastic. Thank you so much, Dave. We are going to get into Q&A here. We've got some good time left to take questions. So with that, we've been getting them throughout, and I'm just going to fire away. So Brian and Dave, these will be for each of you, and I think you'll be able to tell when they came in based on what the question is and who might be best to answer it. But one of the early questions we got, it came along with a comment, was not sure about the rest of the country, but in Pennsylvania, some stream gauges have been taken offline or are being removed from data collection due to funding. And Brian, I know you commented a little bit on stream gauges, but how does that impact the quality of the National Water Model?
Okay, yeah, good question. So we assimilate, we read in and use stream flow observations from the USGS and other sources. we do that for several thousand points across the country, and so if those gauges go dark, that means less data, specifically for those locations. No data for those locations is going to get into the model. So what that means is that there's no correction for model biases in that area. It's just kind of a free-flowing model, if you will. And it would have two different impacts. It would impact the analysis and assimilation cycle of the model, which is our current snapshot, if you recall, basically our best kind of conception or depiction of the current states of soil stream flow across the country. It would affect that directly, since that's where we ingest the observations into. So our depiction of current conditions would be less accurate in those areas. And then also all of our forecasts are initialized with initial conditions from that sort of analysis. And so they'd have a worse starting point for the forecast, which means if you start at a worst point, at a point that's not as good in terms of accuracy, your whole forecast will be less accurate too. So it would have a double impact. Now, if there's other nearby gauges that are still in existence, the impact would be mitigated. But if it's a gauge that was by itself, nothing around, or then you're going to have a bigger impact.
Great. Excuse me. Thank you for that. Just a quick one, and I apologize if you clarified this earlier, but can a FIM incorporate sea level rise too?
So yes, I mean there's so many different ways to calculate a flood inundation map, so many different ways to produce it. But thinking about the way that we intend to produce it, so we would be getting our water levels from some other ocean models, and that feeds into the national water model, and we combine the river flow together, coming in from one side, together with the boundary conditions from the ocean models, external ocean models, kind of meets in the middle within the water model, and we kind of create a total water level, which we can see how far it pushes up onto the land surface then, right, inundation. So as long as our boundary conditions from the other ocean models are incorporating that, then we would see that. So it's an excellent question. I'd have to look at the particulars of the other external ocean models that we're reading from. I would think so. I would think that would be taken into account, but that's the caveat. I'd have to go look for the specific extra models. But my gut feeling is that yes, that would be accounted for, but I would need to double check.
Great. Okay, great. Thank you. And then we got a question kind of asking about where some of our blind spots might be. So the question was, are there prediction confidence analysis occurring so that locations of quote unquote low confidence data or gaps in the data can be identified and priorities set as locations where gauging data, improved hydrography data, ground truthing from past events is needed? So is there anything like that might come to mind?
Yes, that's an excellent question and a good point too. So yeah, something that the foundation of any product, right, is sort of an assessment of its accuracy, because otherwise it's difficult to know how to use it or when you can use it. It's a good point to make. So we have one of the groups in my office, one of the divisions, is running sort of real-time assessments of the model, and they have created sort of extended assessments or look-backs as to how that model's performed over the past 10 days or month or year, and there's some depictions of that. We don't have those posted yet in any sort of publicly accessible forum, but that is something that we're definitely aware of, and working on and trying to make more public, because we realize it's a key source of information, right, in terms of usability. So yeah, that's definitely something that's on our minds and that a particular group is working on. Yeah.
Okay. That makes sense. Thank you for weighing in there. Anne asked earlier, are the outputs of the National Water Model being captured in a database to help inform updates to currently available products such as NOAA Atlas 14?
So the data is being archived in a development database in my office to say inform future versions of the model for comparison purposes. I don't think there's any direct links to NOAA Atlas 14, which is also produced from from my office, a different group. But they are being archived, and again, in the kind of informed version over version improvements, but I don't think that database is informing, I'm trying to think of any kind of another development effort. Yeah, I can't think of anything. It's being used as a springboard to develop enhancements to the model and also new products like flood inundation mapping products. But yeah, I'm not sure if that's a great answer to that question. I can always follow up with email afterwards. But
yeah, great. Okay. Anne actually had a separate question a little bit later on. She says, I noticed the updated land surface for the National Water Model version 3.0 referenced NLCD 2016. And she's wondering if there's a reason why NLCD 2019 wasn't being used.
Sure. Yeah, good question. The development timeline is more extensive than one might think for each version of the model. It takes multiple years to develop each version of the model. So we actually didn't have access to that data set back when we started development of this version of the model. It would definitely something we can drop in for the next version of the model. We release about one version per year, but it's not that each version is kind of cut and dried, just with a 1 year period. It's multiple years that overlap with each other. So we always have a new version coming out every year or two, give or take, but they overlap with each other in terms of development. So it was kind of the data set we had available when we started work on version 3. That's why we were limited to that back.
Yeah. Okay. Yeah, that totally makes sense. Hopefully, Brian will give you a brief, we'll spell you here, but a question for Dave. Who's checking if the discharges trigger alerts? Are they only checking when intense rainfall events occur?
You're muted, Dave.
I saw that. Yes, that's pretty much the way it worked. While we had the project up and running, we were getting alerts all the time. But since then, we really haven't had enough of an alert to get us sort of into the calibration stage. But that being said, Maryland also has a system the DNR put out called MyCoast, where the public can take pictures and we can then calibrate that information. So I think the next phase before we move forward is probably to do some kind of documentation of an understanding of what results are and what we have, and just making sure that we're getting something that's realistically. So I think it's a great question. It's just not part of us through the preparation phase that we had in the pilot that we focused an awful lot of time on.
Yeah. Okay.
Can I add on one just quick thing? So, Dave, I know you're reading in different water model data. Just in general for the audience, I'll say that the most accurate water model output is always going to be the analysis and assimilation, or analysis configuration. That's the one that repeats every hour. And the reason, again, is because it assimilates USGS stream gauge data, but more than that, it's driven by observed precipitation, as opposed to any of our forecasts, which, I mean, obviously they're forecasts, so they can't be driven by observations. And so they're driven by predicted precipitation, which itself has errors. So if you need a forecast, great, but if it's okay to say, look at something in the past or look at just kind of current conditions, the analysis is going to be your best bet, because again, it takes advantage of data assimilation plus precip observations. So just it's kind of a related tidbit I wanted to throw in there. So.
Yeah, thanks for adding that on. Got a question from Stefan asking, is there documentation about how to pull National Water Model flow predictions into GIS?
Yeah, it's a question we get sometimes. There's some basic documentation I could send out. It's not, we don't have a support group, unfortunately, kind of dedicated to user support or user use of this data. If anybody on the line wanted to, if anybody on the line kind of needed help with that, I think I have some text. Basically, I could very brief text I could send along over email. So I'll leave it at that. If somebody wants to reach out, perhaps through I don't know if it could be done through you, Kevin, if you're kind of aggregating, collecting responses, and maybe people could reach. I don't know. Not sure the best way to do it, but I could send along a bit of information. But we don't have a formal help desk, unfortunately.
Yeah, if anyone, I'll be sending out follow-up materials in about a week from this. So if anyone wants to respond to that, looking for the information we were just talking about. Otherwise, as you can see, Brian's email is up on the screen, and you can reach out that way too. So moving along, David comments, false alarms are the anathema of flood forecasting systems. How often does that happen, or how often is there uncertainty in forecasting that way?
Yeah, well, I mean, to be honest, all the time, right? I mean, it's not saying that the system's, bad or any worse than any other weather forecasting system or anything, but, everybody suffers from false alarms or over prediction, under prediction. So this is going to be one of those answers that's kind of maybe impossible to answer specifically, but I'll kind of give a general answer. It depends on what exact location you're looking at. It depends on it varies by event. It depends on the predictability of the event. Depends on just even the antecedent conditions, like what led up to the current conditions before the event happened. That may influence how the prediction goes. And so it depends, if you're looking at the analysis, which is driven by observed precip, so it should be a little bit more accurate, or whether you're looking at a forecast. So I can't answer. There's no one size fits all answer, unfortunately. But some of our operational partners have said the same thing, right? Said that false alarm ratios make it, high FARs make it difficult to use. But of course, you don't want to underpredict and miss events either. So it's a really delicate balancing act. So that's in the standard suite of metrics that we use as we're evaluating each version of the model. We look at CSI, FAR, POD, probability of detection. That's something that we try and improve with each version of the model. So
yeah, that totally makes sense. This one's for Dave, and I'll make a brief comment after I ask you this, Dave, but is all the data and models you presented available and accessible online for Maryland? And I just want everyone to know that we are recording this, and we'll be making the recording of the presentation available. But I did want to ask you, Dave, if it's already out there.
So Kevin, I responded I typed my answer. Do you get those, or do I have to do something else with them?
I didn't see it.
I'll answer it again. That's fine for everybody else.
Yeah.
So in Maryland, there's 24 counties, and basically 23 of them had a full update or are in the process. So in those 23 counties, we've posted every FEMA model online, and you can download them, whether they're our best available data or they're the actual detailed model for the state, for the riverine areas. There's one county that has their own sort of GIS and CTP arrangement with FEMA. That's PG County, and I'm not, throwing them under the bus, but they're not sort of georeference models like the rest of Maryland. So I have a hard time publishing them with the GIS data sets that are there. So in Maryland, if you need data in Prince George's County, you go to them and get the best data that we have. But in Maryland, we try to keep those current and up to date. And we have a system in place for updating any models that get updated, but at the same time, it hasn't been used very rarely, like to date in the last 12 or 15 years. It's kind of funny that there's development going on, but the FEMA models, we probably need to work with the national FEMA data set and get LOMARS and like LOMAX updated into the system. What was the other part of the question?
All right, great. Thank you, Dave, for answering that for the group. Sorry, I didn't see the typed response earlier, but we've got a couple of questions, maybe naturally about how the model might work with Hurricane Ian. So Al asked just that question. He said, have we tried running the model on Ian? And we also got a question, are the stream flow projections for Florida able to take into account Hurricane Ian? So it's obviously an ongoing event. So I was just wondering if you could comment on that.
Yeah, sure. Yeah, current events are always, make for interesting insights, right? So,
yes.
So the current operational version of the model, it's running all the time, 24/7. And so, yes, it's running operationally right now during this event, kind of day in, day out. The current version of the model does not have that coastal coupling. It does not have any notion of the ocean or what's going on in terms of storm surge or tides, things like that. That's for the next version coming out next summer. That'll be version 3. So the current version only knows about freshwater flooding. By that I mean rainfall. So it certainly knows about and is simulating the stream flow impact, soil moisture and stream flow, et cetera. All that runoff that's happening from the 1 feet or 2 feet of rain, that's fallen over Florida, and it's pumping out, hydrographs. Well, not, it's pumping out stream flow values, which you can visualize in different ways across the whole country, including, of course, Florida. So some of that information is used by my office's operations center, and then they coordinate with local weather forecast offices down in Florida and other places, along with agencies like FEMA and the Army Corps of Engineers and others. Those, draw in information from, from the water model and, many other sources to kind of pull together the official response and forecast. So we're just kind of, we're a part of that information stream, you might say. There's a lot of sources that everybody draws on.
Okay, great. Well, so we do have a couple of questions left, but we also only have a couple of minutes left. So what I'll do is move on, and we're going to ask everybody to rate our event today, and then I'll make a few brief closing comments. But for the questions that are outstanding, those of you that have asked those, we'll definitely try to get answers to them, and then get the answers to you in writing. With all the other promised follow-up materials. So thanks for your patience on that front. Last thing I'll do here, I need to open our poll, and just please briefly weigh in on what you thought of the presentation today. I'll leave this open for a few more seconds, and then I'll make some comments just about what you can all expect in the next week or two. Okay. So I mentioned this briefly at the top, but just to reiterate, if you hung out with us the entire time, you participated in the polls and so forth, you will be eligible to receive continuing education for this event. So we'll be sending you certificates of attendance and adding those CECs to your records. It may take up to 2 weeks, but probably about a week from now, you should expect that in your inbox. So just please look out for that. And then I just want to, of course, say thank you to Brian and Dave for taking the time out of their schedules to present this material to us, and thank all of you for joining us for the full duration. If you have any future suggestions for topics we might present on, you can send those to Alan. But other than that, we'll get the certificates of attendance to you, and the recording will be made available, and we look forward to speaking to you all next time. Have a good afternoon, everybody. Take care.